Hello and welcome everyone to your first Chem 4 lecture. This is the general organic and biochemistry class. Hopefully by now you've watched the welcome video, you've seen the syllabus video, and perhaps you met me in person in lab. But this is the first lecture as we're going to have them online this semester. So we're going to start with chapter 1. And we're going to talk briefly through chapter 1, mostly just introducing the concept of what is chemistry, like what you see on the slide here, and then trying to make sure that it relates in person to you for what you're going to use it for in the future, which we're kind of assuming is mostly allied health. If you're liberal arts, then we're going to study on how chemistry affects the body. And so that's kind of the point here, is that we're starting with an introduction to general chemistry. Then we move into a small piece of organic chemistry, and we need to understand that organic chemistry so that we can understand biochemistry. And ultimately, biochemistry is the main goal of what we want you to learn is this semester. And it's what's going to set you up well for your future in the health, in whatever health field you happen to be working in. So that's the goal this semester. And so we're going to start just with chapter 1 from the beginning, trying to understand what is chemistry and then how does it affect us, and specifically for your future. So the book definition of chemistry is that it's the study of matter, which is, its composition, how it's built, its structure, how things are related to one another in, physical space, the properties of matter. So how do things react? Why do they look the way they do? Why do they interact with each other, in different ways? And then the chemical reactions, of course, which is a big part of what we'll study this semester. And the thing that we want to kind of point out here is that chemistry happens all around you every day. And, on a fundamental level, if you kind of look, for example, in your body, you look closely enough on the fundamental level, what's happening is chemical reactions are constantly churning in your body, in every cell, whether that's, replication of DNA, whether that's transcription of RNA, whether that's, you're building proteins. These are all hinging on chemistry. And so this understanding of chemistry hopefully will inform you of what it is that makes us tick, at least on a chemical level and biological level. We'll kind of build it, you'll let your biology courses build it from there, but we'll at least give you kind of a fundamental view of what goes on with things like metabolism and that. So as we mentioned, we've got composition. That's, what is matter made of? Matter being, everything that you see around you, whether it's, the table that I'm, on here. Is it the laptop or phone that you're looking at this video from? The air that you're breathing is also matter. Basically everything is matter. We also talk about the structure of matter. How is it put together on a fundamental microscopic scale? What characteristics does it have? And then finally, how does it react or behave when you put it with other substances? So okay, I basically already told you this here, so I kind of skip ahead sometimes on that. One reason that we're doing this for the for recorded lectures this semester is in the past we found that actually having these recorded lectures available for students allows you to pause the lecture when you need to take notes. You can rewind and hear what I said. And if you want to copy this down, these slides are posted on our Canvas site. So if you want to just print out the slides and write on the notes, totally fine. If you just want to have the digital file and write on those notes, totally fine as well. Whatever you're kind of most comfortable with is the idea. But as you'll see, kind of sometimes I talk a little bit ahead. So in this case, if you want to go back and listen to what I said, make sure that you got it all down. But this is just kind of showing you here how chemistry relates to everything that's around us. So we showed the antacid tablets on a previous slide. Those are matter, water, oxygen, carbon dioxide. All of that is matter. It's made of atoms, as we're about to find out. We're made of matter. So anything that's matter is made of chemicals. So these are substances that have the same composition and properties wherever you find them. So carbon dioxide in your cells has the same properties as the carbon dioxide in the air. Same with oxygen. As you bring it in, it's the same as what you had in the air, of course. And Yeah, these are basically everything that you're going to interact with. So we have the example here of toothpaste. So um, if you ever forget your phone when you go to the bathroom and you look for something to read, toothpaste is a really good one because there's a lot of ingredients in it. And I think I wrote them down here. Yeah. So for example, it's made up of things like calcium carbonate, sorbitol, sodium lauryl sulfate, titanium dioxide, sodium fluorophosphate, methyl salicylate. Each of these chemicals, adds together in the toothpaste to give like a different function. So calcium carbonate is a solid, is basically limestone. And so that's used in the toothpaste to kind of act as like a scratchy surface. So it removes the plaque from the outside of your teeth. We're not going to go through all of these here, but just to give you an idea, sodium lauryl sulfate, we're going to talk about fatty acids towards the end of the semester. And that's an example of a fatty acid that acts as a soap, essentially. Or it's a relative of a fatty acid, I should say, to be totally distinct. And then methyl salicylate is an ester. That's an organic chemical, and that actually has a flavor to it, a minty flavor, like wintergreen. So that just kind of gives you an idea of like why it is when you look on the back of whatever you happen to be, whatever you're eating, or soap or shampoo, you'll see all these different ingredients, and all these different ingredients kind of combine to make the one product that we use. Okay, so all right, this is our first example of what I call a sample exercise. Because of the first chapter, I forgot to change the title from learning check to sample exercise, but this is going to be available to you on a PDF down below in this Canvas discussion. Go down there, you'll see a sample exercise for chapter 1. Go ahead, print that out if you want to. If you'd like just to download the file and manipulate it on your computer, that's fine too. But this is going to be just a way of like following through the lecture, and we'll have the answers to it right after this. So we just kind of like have a way of kind of, while you're watching the lecture, learning about the lecture as you do it. So here we go. So learning check. Which of the following contains chemicals? We got sunlight, fruit, milk, or breakfast cereal. What do you guys think? Which of the following, and can be more than one, contains chemicals? So in this case, for sample exercise, I'm going to recommend pause the video, think it through, come up with the answers on your own, and then we're going to go through the answers together. So this is a great opportunity. Pause the video, and then when we come back, we're ready for the answers. So let's go through it. So hopefully you figured out the trick of this one, which is that anything is made of matter, but sunlight is kind of the weird one here. Sunlight is energy that comes from the sun in the form of electromagnetic radiation, and that actually doesn't contain any chemicals. It's not matter; it's energy. So this is one thing that we're going to kind of introduce in this class, is the duality of matter and energy. We're going to talk a lot about how they're related to one another and how they affect one another, but we keep them separated. There are distinct things. Matter is made of chemicals. Energy is its own thing. However, fruit, milk, and breakfast cereal all contain chemicals. They're things, they're objects. So all of those are made of chemicals. Okay, so this may be your first science class in a college setting. Maybe you've been introduced to these types of ideas in the past about scientific thinking, but we want to kind of introduce the idea of science, like what distinguishes scientific study from other studies. And that is what's called the scientific method. Now, we're going to give you like a rote example of the scientific method. You may have learned it slightly differently in other classes. The main thing is that scientific method involves kind of a loop of experimentation and theorizing, let's call it, and then doing more experiments to improve the theory that you go back to. So we have basically four basic steps for the scientific theory, or the scientific method, excuse me. And this is just going to give us a general idea of how we should think critically like a scientist. So step 1 is you're going to make observations about whatever phenomenon you happen to be looking for, and then you're going to start to ask questions about what it is that you're observing. When you have a question that you want answered, what you want to do then is propose what's called a hypothesis. Now, this is just your idea. It's kind of what we call like an educated guess to, using your knowledge, you think, okay, this is a likely explanation for what I'm seeing around me, this observation. But that's not where we stop. The crucial part is the next part for the scientific method, which is that you try to explain it and then you test your explanation for your observations. And this is what we call experimentation. So the experiment is just a test, and you just think of a way of like testing what you believe is true by trying to disprove it. Basically, that's the way I always say is that a good experiment should be designed to disprove your hypothesis. And you go through a series of these until finally then you can analyze your experiments. You make a conclusion about your hypothesis. The hypothesis is either it gains evidence in the form of your experiment, or you've disproven it. It's been made false. And then it goes through kind of a cycle of experimentation followed by hypothesis, and then follow that up with experimentation, followed by hypothesis, et cetera, until you finally get to a conclusion. Once you have kind of enough experiments and evidence, then you're ready to state your theory of what it is that you're observing. Okay, so let's give an example of this type of scientific thinking and how you could use it every day. So if you were to go visit your friend and you noticed that you had your eyes watering and you started to sneeze and you noticed your friend has a cat, that's just an observation. You visited your friend, they have a cat, and you had some kind of reaction. You were crying, you had sneezing, some issue like that. That's just an observation. Hypothesis one. Well, maybe you're allergic to cats. You had an allergic reaction to your friend's cat, and that caused you to have that reaction that you did. So what's the first experiment you could do? Well, you may go ahead, leave the house and try to get away from the cat, and then see if you recover. If you recover, then okay, perhaps that could still be the cat, then definitely. If it doesn't stop, if you're still crying, you're sneezing, maybe you have a cold. Hopefully not, but you never know. Now, if the itching and sneezing stops here, this is where I want you to kind of think critically about the scientific method is, if this is if the itching and sneezing stops, is your hypothesis true? Is it necessarily true? Not necessarily. You just did one experiment and you know that at your friend's house, you have an allergic reaction. But it doesn't necessarily mean it's the cat, right? I mean, if you leave and your allergic reaction goes away, that means that there's something at that house that could do it, but it doesn't necessarily mean it's the cat. Don't automatically blame the cat. So what you have to do then is try another experiment where you're now testing cats. Maybe you go to a cat cafe or another friend that has a cat. Is my cat here? He's not here right now, but so visit another friend with a cat and see what happens. If you then start sneezing and your eyes start watering again, that gives another kind of evidence that, oh, hey, I might be allergic to cats. And so this is a pretty good indication then that your theory of your being allergic to cats is a pretty solid theory. Now, if you want to go next level, you go to like a dermatologist or some specialist, allergy specialist, and they can do tests on you and say, oh, sure enough, yeah, you're allergic to cats. And that would be kind of another piece of evidence. You see, you can keep experimenting until your hypothesis, becomes more valid. And then that's when it kind of graduates into what we call a theory. Okay, so now what I want you to do, this is our sample exercise number 2 for chapter 1. Go ahead and for each of the following, just classify A, B, C, D, and E as either an observation, a hypothesis, an experiment, or a theory. So again, let's go ahead and pause the video. You go through these, classify each of these statements. So like a blender does not work when plugged in. Is that an observation, hypothesis, experiment, or theory? Classify each statement A through E. And then when we unpause the video, we're going to go through each of them together and make sure that we understand what's going on. So take this opportunity to pause. And we're back. Let's go ahead and take a look. So first off, we have A blender does not work when it's plugged in. Well, that is an observation, right? You plug in the blender and you try it. That's not it's not working. That's just you're noticing, oh hey, the blender's not working. Okay, so then we have B and C, which is B is the blender motor is broken. That's an explanation. That answers the question, why is the blender broken? That's our hypothesis. And then C, the plug has malfunctioned, or the outlet probably is the better way to say it, the plug malfunctioned. So that's an example of a hypothesis as well. So we have two separate explanations. Then we take the blender and we plug it into a different outlet. That's an example of an experiment. We're testing basically the outlet theory that we had from C, where we had the outlet was malfunctioning. So we plug it into a different outlet, still not working. That's a pretty good indication that we need repair. We need to repair our blender. And that blender needs repair is kind of a theory, or a conclusion is really what we would say there. So this is just kind of giving you an everyday idea of what scientific thinking should be like. But definitely let me know in the comments below if you have any questions, or via email, whatever is most convenient to you. Okay, so we're just going to go briefly through this section. This is mostly like how to use your book section. So we have the Timberlake General Organic and Biochemistry text book, and they have just a few kind of features as you're reading the book that you want to notice and kind of use. So this is just going to like help you a little bit. We're going to do some more of this type of stuff at when we get to lab. If I haven't seen you already in lab, we're going to do it in lab. If not, then you've already seen what we're working on, as far as like making sure that we're scheduled and we know how to prepare for each quiz and each test that we're going to have. So yeah, so these are just some general tips for your study habits. You don't just want to be rereading the text or just rereading your notes, because you want to make sure that you're developing like a critical or a deeper understanding of the material itself. So the way that you're going to do that is you're going to ask yourself questions as you read, and those questions are going to kind of plumb the depths of your knowledge and make sure, oh, I really understand this on as fundamental a level as I need to. There are practice problems in the text, and you can use those to give yourself quizzes at the end of each section and at the end of the chapter. I have some of the practice problems listed in the syllabus. So at the end of the syllabus, you'll see the practice problems available there. One reason that we're doing the scheduling the way that we did in the lab is that we want to make sure that you're studying at a regular pace rather than cramming everything in. This class is a marathon. It's not a sprint, although it actually goes pretty fast. So it's like a marathon where you're really working really hard. But that's why we're scheduling it out now, so that you're more kind of comfortable with your work each week. And then finally, we're going to relate new concepts to the concepts you already know. Now, your book does a really good job of kind of highlighting with concept maps at the end of each chapter how concepts should be related to one another. And you just want to make sure at the end of each chapter, look at that concept map, make sure it fits with your web of knowledge. Okay, yeah. Oh, so just a few things here. Again, this is from your textbook. So I just want to like kind of point these out before we start the semester and we get too deep into the reading. Note key math skills here. Those are reviewed in your chapter, in your textbook. I know many of you may be at different levels of math. Like some of you may have taken your college level math classes already. I know we have a basic prerequisite for that math skills, but it's always good to review and just kind of make sure you know what you need. We're not going to try to hit you too hard with that, and I'll make sure to review them as needed. But just make sure that you're aware of that when each chapter rolls around. Okay, then we have core chemistry skills. That's outlined in the text with this magenta, I guess, highlight here. And that's going to be kind of noted in the text and then summarized at the end of the chapter. And then finally, there's a review section for each of the key math skills and core chemistry skills that you need for that. And then, so the engage is kind of an interesting part here where it's like trying to connect it again. One of the reasons I like teaching this class is that it really connects closely with the health field, and what's more important than taking care of people and making sure that people are healthy. That's kind of one of the fundamental applications of chemistry here, and that's what we want you to have familiarity with. And so this engage is like making sure that you're engaged with the material and you kind of understand what that means on in everyday life. And then test. So this is where it's like, this is a pretty good indication of what your book thinks is important for the test. I'll definitely let you know if I disagree with it, but it's mostly true that whatever you whenever you see one of these test things, just give yourself like a little quick comprehension check, make sure you understand what's going on. And then finally, interactive video would be available online, or I think if you have the e-text, you can just click a link basically, and you'll have the interactive video there. Okay, so yeah, so note here, this is kind of one type of figure that you're going to see a lot of, where we have a macro illustration and a micro illustration. So macro means macroscopic or large seeming. In other words, that's how we see things every day, as we're walking around just with our eyes, for example. But in chemistry, we want to understand the relationship of the microscopic to the macroscopic, or what is happening at the microscopic level to produce this macroscopic effect. Well, this is aluminum foil here. Aluminum foil, aluminum can be shaped into a foil because it's a very malleable material, where you have, these atoms can form very thin layers on top of each other, yet still be connected together using metallic bonds. And this is just kind of, again, a general idea of like, this is what we see on the macroscopic level down here. We're going to look into the super microscope, we'll say, with and see the atomic level. And that way we understand the chemistry behind it. Okay, yeah, so this is all still in your book here. Yeah, and make sure, of course, you're always using practice problems, as we mentioned already, and then the concept maps at the end of the chapter. So again, your book is going to keep you kind of on pace here, and I strongly recommend making good use of the book as we go through the semester. Yeah, okay, so making a study plan, this is what we're going to talk about in lab. Make sure that you're kind of aware of it. These are some of the good ideas that you have here. And we'll talk about all of these when we're in lab together and we're going through the study plan activity. So we don't need to go through this again. It's just in the lab. Here we go. Okay, got it. All right. So here we're going to talk about a few different key math skills that we're going to need for chemistry this semester. And these are just kind of reviewing some of the words that we've used in the past in our math classes, and we're going to bring it into chemistry. So, and into our science classes, because a lot of what we're doing is we're doing a lot of measurements, and then we're doing a lot of conversions. So it's a lot of using mathematical operations in maybe a slightly different way than what you're familiar with before. We don't just have numbers now, we have measurements, and those measurements we need to kind of keep intact. So just reviewing some words that hopefully kind of make sense here. So, okay, first thing is that we want to make sure we understand place values or digits. So remember, if we have a number like 2,518, we have 4 different digits in 4 different places. The 2 is in the thousands place. Does that sound familiar? And then the 5 is in the hundreds place. The 1 is in the tens place. And the 8 is in the ones place. Then if we were to go into, let me see, I think it's here. Okay, so now here, 6.407 grams. Well, 6 is in the ones place. The 4 now is in the tenths place. The 0 is in the hundredths place. And the 7 is in the thousandths place. So just kind of keep remembering that, tenths, hundredths, thousandths. Again, it may be something that you learned a long time ago, but we're going to be, using these terms all the time. So you just want to kind of make sure that vocabulary is in your vocabulary. If that makes sense. Okay, so now let's go ahead and try to identify the 15.24. Go ahead and identify the place value for each of the digits in 15.24. Again, this is in our sample exercise packet, sample exercise number 3 now. So go ahead, tell me for 15.24, what are the place values for each of those digits? You can pause it now if you need a little bit of time. But if not, let's pick up. The 1 here in the 15.24 is in the tens digit. The 5 is in the ones digit. The 2 is in the tenths digit. and the 4 is in the hundredths digit. Okay. So again, if you need any help with that, just make sure to reach out to me. This is, again, something that we're going to be using constantly all the time. So good to review it now that you have a little bit of time. Okay. So next up, we have positive and negative numbers. So remember, positive numbers are greater than 0. Negative numbers are less than 0. The negative number is usually written with is always written with a negative sign. Just so you know, positive numbers usually not written with a positive sign. Usually, instead of positive 8, you're just going to put 8. And remember, when you multiply two positive numbers or two negative numbers, you get a positive answer. So a positive times a positive gives a positive answer. A negative times a negative gives a positive answer. On the other hand, if you multiply a positive times a negative or a negative times a positive, you get a negative number as a result. The same thing is true with division, where if you take a positive number and divide it by a positive number, you get a positive answer. And if you take a negative answer, a negative and divide it by another negative, that also gives a positive answer. On the other hand, if you divide a negative number with a positive number or a positive number with a negative number, that gives you a negative answer. Okay. So when you add two positive numbers, you have 3 plus 4 gives 7. No problem. Again, we're assuming the positive sign here for most of our math. A negative number is always going to be shown with a negative sign. When you add two negative numbers, you're always going to have a negative sign. So negative 3 plus negative 4 gives you negative 7. Okay. When you take a positive number and add a negative number, this is an interesting way of doing this. So this is, addition with positive and negative numbers. You may have a different way of doing this. The way that I've always done this is that if you have a positive and a negative being added together, you take the positive and you subtract the negative. So like I would enter this into my calculator as 1, 2 minus 1, 5, and that would give me negative 3. Now it's true also, you can use your calculator and say 12 plus 15 negative. That gives you negative 3. Either way, totally fine. Now the way your book says here is that you take the smaller number, subtract it from the larger number, and the result has the same sign as the larger number. That's fine. I don't think that's really, that's not really understanding what's going on here. I think there's an easier way to do it, which is, what I was just saying. It's 12 minus 15, or 12 plus negative 15. Either way, totally fine. This is also a really good chance to go ahead and get your calculator out, your scientific calculator that you need for the class, and just practice your addition and subtraction. And make sure that you're able to add those numbers and subtract them and multiply and divide using your calculator. I know your book has some additional practice there as well. Okay, so now one thing that we're going to do a lot this semester is we're going to calculate a lot of percentages. So when you take the percent of something, you're going to take the part of something that you're interested in, divide it by the whole, whether that's mass or volume or weight or whatever it happens to be, and then you multiply it by 100%. So the way this works is, okay, so here we go. An aspirin tablet contains 325 milligrams of aspirin, and the tablet has a mass of 545 milligrams. What is the percentage of aspirin in the tablet? So first up, make sure that your units are the same. I'll talk a lot more about this in the next chapter. We have 325 milligrams of aspirin in 545 milligrams of a tablet. So the part is the 325 milligrams. The whole is the 545 milligrams. So we take the part, divide by the whole, times 100%. Our answer comes out to 59.6% aspirin. Again, a percent is something that we're going to do again and again and again. So we just want to make sure that we're familiar with this. When I ask you to take a percent, you'll be able to do it very quickly. And again, the idea is here basically a percentage is going to give you the number of parts in 100 of the total whole. So if you say that a mixture is 5% of red balls, well, that means that for every 100 balls, you'd get 5 red balls. If you had 50% green balls in the mixture, well, that means for every 100 balls you'd have 50 green balls. Okay, So that's percentages. Make sure that you're kind of familiar with that. There's, again, more practice on this in chapter 1 in your book. So strongly recommend, if you're feeling a little nervous about that, there's a lot of good examples there. And then bring it to me and I'll review it with you when we're in lab together. Okay, so next up we have a little bit of algebra. So remember, big part of algebra is being able to solve equations. For example, here we have 2x plus 8 equals 14. And the idea is we want to manipulate this equation so that we can solve and determine the value of x. So given this, 2x plus 8 equals 14. How do we solve for x? That's our unknown variable. So the first thing that you have to do is you have to place all the like items on one side. So we have an x item and then a constant item, which is just the 8 and the 14. So we need to get the numbers, the 8 and the 14, to the same side. How can we do that? Well, we could subtract 8 from both sides, or we could subtract 14 from both sides. In this case, it makes sense to move the 8 to the right side. So we're going to subtract 8 from both sides. That's going to give us 2x plus 8 minus 8 equals 14 minus 8. Then do the calculation. Plus 8 minus 8, of course, is going to be 0. So we get 2x. 14 minus 8 is going to be 6. Next, we want to isolate x. And here we have 2 times x. So to get rid of the 2 multiplier, we need to divide both sides of the equation by 2. So if we divide 2x by 2, then we also have to divide 6 by 2. We solve for x, that gives us x equals 3. Remember, whatever you do to one side of the equation, you have to do the exact same thing to the other side. That's why we minus 8 and minus 8, left and right. And then we divided both the left and the right side by 2 after that. So that's how we would do it. Finally, you can check your answer by plugging in the solution that you got. Plug in 3, 4x, and just make sure that it actually is a valid answer. Okay, so why don't you go ahead and give it a try. This is now sample exercise 4. Go ahead and try to solve for P1. This is a gas law problem that we're going to learn about later this semester, where the pressure times the volume of one sample is equal to the final pressure times the volume of that same sample, given a constant temperature amount. So given that, go ahead, solve for P1. We want to get the equation for P1. Go ahead, pause the video, and when we come back, we will have the answer ready for you. So go ahead, pause. Let's take a look here. So we have to get P1 alone. Now P1 here is multiplied by V1. To get rid of V1 from the left side, we need to divide the left side by V1. Well, if we divide the left side by V1, we also have to divide the right side by V1. So we divide both sides by V1. V1 goes away on the left. That gives us P1 equals P2 times V2 divided by V1. And that's our answer. Let me know if you're having any trouble with that in the comments below. Okay, graphing. Now, graphing is another mathematical skill that we're going to use a lot this semester, especially in lab. So we're going to kind of emphasize the ability to display data in the form of a graph. And this is something that's going to be extremely useful to you in your future career as a medical professional. You're going to look at charts and graphs a lot for a lot of different patients. And so we want to make sure that when you see a graph, you're able to quickly identify what it means. And then also you can, once you know what it means, how to translate it, you'll be able to identify any troubling spots or any abnormalities that you might see in your patients. Okay, so for example, this is a relationship graph between the temperature of a gas and the volume of that gas, and the volume of a balloon in particular. And what we note is, as we increase the temperature from left to right, the volume of the gas increases as well. So the volume, that's the y-axis, that's our vertical axis. The temperature in degrees Celsius, that's our horizontal axis, or the x-axis. Yeah, so you just want to note here that again, your vertical axis is the y-axis. You labeled it in terms of volume in liters, and you have the temperature in terms of degrees Celsius. Another thing that's very important for graphs that can be easy to kind of lose track of here is that your axes have to have a regular intervals. So in other words, we know each square here increases by 20 degrees Celsius. We go from 0 to 20, then 20 to 40, 40 to 60, 60 to 80, 80 to 100. Same thing with the vertical axis. We notice we go 22 to 24, 24 to 26, 26 to 28, 28 to 30. So each interval here represents 2 liters. So the x-axis is 20 degrees Celsius per interval, and then the y-axis is 2 liters per interval. Yep. Okay. So one thing that we note is when we do plot this, we see that if we form a straight line here, this is what's known as a direct relationship. As we increase the temperature, the volume increases, and it's you just get a line relationship there. Okay. Again, if you're unfamiliar with graphing, we're going to have a lot of time to practice it in lab. So please make sure when I'm walking around the lab, when you have any questions, just make sure, ask right away, hey, Professor Dowd, I need some help. I'll come right over and we'll make sure that you're plotting out your graphs correctly. One thing to note here, and we'll talk about this in lab as well, is this is kind of like a perfect graph where you have perfect data and the best fit line just goes right through it. What you're going to find is in lab, you're not going to actually have perfect data. You're going to get data points that kind of like, are a little rough. And then you'll draw the best fit line through them to the best of your ability using a straight edge. So note, the line doesn't have to pass through every point. That's just kind of like in a perfect world, or if you have a really good relationship and a really good measuring instrument. Okay, so I think this is one of the last ones here, scientific notation. Now, this might be new to you. I'm not totally sure if they teach this in your math classes or not, but in chemistry, we deal with atoms. And so there's two main things here, which is that an atom itself is very small. So if you were to try to like weigh an atom, you're going to get, 1 times 10 to the negative 22 grams. So it's just a tiny, tiny, tiny number. If you're trying to like speak it out, it'd be 0.00000000000000001 grams. And if you try to write that out, that's just going to take forever. Like that's not a useful way, to use your time in the class. So we come up with scientific notation as a way to write these really small numbers. Now, it's also important because what if I give you like a gram of copper and I ask you, hey, how much copper is in here? How many atoms of copper are in here? Well, you can do the math, but it's going to be a tremendous number of atoms. It's going to be on the order of, again, 10 to the 21 to 10 to the 22. So it's going to be, that's a lot of atoms that you have to deal with. So again, a very big number in that case. So just because we're dealing with things that are so small, sometimes we have very small numbers, sometimes we have very big numbers. And so scientific notation is going to help us write and then manipulate those numbers in equations as we need to. So to give you an idea here, just starting from hair rather than diving straight into atoms, human hair has a width of an average width of 0.000008 meters, which could be written as 8 times 10 to the negative 6 meters. That's an easier way to write it. Takes a lot less time once you understand, of course, how to use scientific notation. And then because, again, these are so small, how many hairs do you have on your head? Well, it's on the order of 100,000, which would be, again, a big number, or you could write it as 1 times 10 to the 5th. So let's review how we do this. Scientific notation, any number that's written in scientific notation is going to have 2 parts. We've got the coefficient, that's the numerical value, and then we have it multiplied by a power of 10. This coefficient is always between 1 and 10. So there's never like a 10.2 or a 12.2. If that were the case, then 12.2 would become 1.22, and then that would change the power of 10 that we had to multiply it by. Okay, so here's how we do scientific notation. If you have a big number, like 2,400, you want to write it in terms of scientific notation. What we do is we take the decimal place. No, 2,400, the decimal place is after the second 0. To get to our coefficient being between 1 and 10, well, we have to move the decimal over 1, 2, 3 places. And that gives us now 2.4. So the coefficient or numerical value is 2.4. We move the decimal 3 places to the left. So what that means is the power of 10 is positive 3. The way you can think of this is it's 2.4 times 10 to the 3rd. 10 to the 3rd is just another way to write 1,000. So it's 2,400 or 2.4 times 1,000, which is 2,400. Again, we're not changing the value of the number here. We're just changing the way that it's displayed. I hope that makes a lot of sense. I hope that that kind of becomes clear here. But again, 2400 equals 2.4 times 10 to the third. These are the same number, just matters how we want to write it. Now, on the other hand, let's say that we have a number that's a lot less than. If we have a number a lot less than 1, for example, 0.00086, well, the decimal place here, we need to move it in between the 8 and the 6 to get our coefficient. So we move it 1, 2, 3, 4 places to the right. Now, when we move it to the right, that means that we have a very small number. So that means that our power of 10 is going to have a negative number here. So it's a negative exponent. So because we moved it 4 places to the right now, that means our power of 10 is going to be 10 to the negative 4. And our coefficient, again, we ended up at 8.6 because it's always going to be between 1 and 10. We're just going to move the decimal over until we have it behind that first number there. Okay, so just to give you an idea here, these are your powers of 10. 10 to the fourth is 10,000. 10 to the third is 1,000. 10 to the second is 100. 10 to the first is 10. 10 to the 0 is, 10 to the 0 is 1. And so the idea is here, the 0 power of any number gives you 1. If you have 0.1, so the 10th digit, that's 10 to the negative 1. 0.01, the 100th digit, is 10 to the negative 2. 0.001, that's 10 to the negative 3. And then the 10,000th digit, that's 0.0001, that's 10 to the negative 4. So again, just kind of reviewing these powers of 10 because we're going to use them a lot in scientific notation. Now, to give you an idea why this is important, well, let's look at some of the numbers that we may need to review throughout a semester. So if you were to ask yourself, how much gas is used in the United States each year? Well, we would probably answer in gallons, but if we were to measure in terms of liters, it would be 550 trillion. So that's, so thousands, millions, billion, 550 billion liters of gasoline. And now that's a big number to write out. So you could just write out 5.5 times 10 to the 11th liters. What about the diameter of Earth? Well, Earth is pretty big, right? So it'd be 12,800,000 meters. If you write in scientific notation, a much easier 1.28 times 10 to the 7th meters. What if you were asking, oh, hey, what's the mass of this bacteria? Well, it's on the order of 0.0000000000000000001 kilograms. That's an extremely clunky way to be able to write that mass. So instead, use scientific notation. It comes out as 1 times 10 to the negative 19 kilograms. And so that's kind of the idea here with scientific notation. It's going to be extremely useful for us to do that. So this is just, again, kind of giving you that idea. Chickenpox virus, we didn't go over that number on the previous slide. Standard format doesn't give you much idea. 3 times 10 to the negative 7 is much easier to write and then much easier to communicate with respect to this measurement. Okay, now here's going to be a crucial thing. And if you're having trouble with this part, this is a part that I might need to help you out in person. So make sure to grab me in the lab and say, hey, professor, I was having trouble with scientific notation, entering it on my calculator. But hopefully we can kind of explain it to you. Because here's the deal. Scientific notation is also easier on your calculator. So that's another big reason to get adjusted to it as quickly as possible. Okay, so let's say that I ask you to enter in your calculator 4 times 10 to the 6th. Now, if you were to go into your calculator and do 4 times 10 raised to the 6th power, you have to click 1, 2, 3, 4, 5, 6 buttons. But in actuality, you only need to click 3 buttons. There's 1 for 4. Okay, so you need to click 4. That's the coefficient. Then you click this button here. Look on your calculator for either a double uppercase, double capital EE, or sometimes it's EXP. Also, sometimes you'll see it as times 10 raised to the power of. Rarely, it happens. And then press 6. So that gives you 4 times 10 to the 6th. And your calculator will display it, in a number of different ways here. But that's going to save you so much time. And again, if you're having trouble finding this on your calculator, just let me know and I can help you find it, no problem. The same thing is true with negative coefficients. The only difference is here you're going to add in an extra step where you have the negative 4 in this case. So you click -4, or you could also click 4 negative will work on most calculators. Yeah, so then also obviously your calculator is going to display it a little differently depending on which brand you have. But if you have 7.52 times 10 to the 4th as an answer, well, that's going to show up on your calculator as 7.52 E04. Again, just telling you this is times 10 to the 4th power in this case. In this case, 5.8 E0 -02. That's your 5.8 times 10 to the -2. We'll play around with our calculators a little bit in lab, and that's going to make sure that you're understanding what this looks like on your personal calculator, and it's going to help you out a lot for your calculations this semester. Yeah, and also, if you are looking at your calculator, you can make your calculator display as scientific notation. If you look for this capital SCI, so sometimes it's one of the buttons you can press like the second function or third function, and you see an SCI, and that'll make sure your answers are always displayed scientific notation. Other calculators, you have to dig into the settings, and it'll say, do you want it in degrees, radians, gradients, and then there's another like float or scientific notation. You're looking for sci, SCI, either way. Again, if you're having any problems with that, just let me know. I'll make sure that you can find it. Okay, so here's our last sample exercise for the chapter. Go ahead, write each of these in scientific notation. 64,000 and 0.021. So pause the video, and when we come back, we're gonna have the answer. Let's go ahead and pause. And let's take a look here. So we have 64,000 first. Now we know the decimal is at the end of the 64,000. So we're gonna move over the decimal 1, 2, 3, 4 places to the left. So we end up with 6.4 as our value. Then we know it's going to be multiplied by 10, and we moved the decimal 4 places to the left. So it should be 6.4 times 10 to the positive 4th power. So in other words, 6.4 times 10 to the 4th. For 0.021, on the other hand, this is a number that's smaller than 1. So we know it's going to have a negative exponent of 10. So we take the decimal, 0.021, move it 2 places to the right. We get 2.1 as our coefficient. And then we end up with, we moved it 2 places to the right, so it's going to be -2. So 2.1 times 10 to the -2. Okay, very last one here. Write the correct scientific notation for each of these. 0.000008. Is that 8 times 10 to the 6th, 8 times 10 to the -6th, or 0.8 times 10 to the -5? And 72 million, is that 7.2 times 10 to the 7th, 72 times 10 to the 6th, or 7.2 times 10 to the -7? Go ahead, pause, make sure that you got your answer right. Take a look here. All right, so for A, the answer is 8 times 10 to the -6. You need to move the decimal 6 places to the right. 1, 2, 3, 4, 5, 6. So moving it 6 places to the right means it's 10 to the -6, and your coefficient is just going to be 8. For here, we're 72 million, we're moving it to the left. 1, 2, 3, 4, 5, 6, 7. So we know it's going to be a positive exponent of 10. So it's 10 to the 7th, and we end up with our coefficient of 7.2. So 7.2 times 10 to the 7th. Okay, hey, you did it. You made it to the end of chapter 1. Now, this was probably mostly reviewed. Maybe there was some new stuff with the scientific notation, but starting with the next chapter, we're likely into a lot of new stuff. So make sure that you're prepared. Obviously, coming to lab, that's number 1. Watching these lectures. If you have any questions at all, make sure to comment in the lecture link down below in the Canvas discussion, and I'll get back to you right away. So until then, until the next lecture, I will see you soon, and let me know if you have any questions. All right, bye-bye.